everybody, welcome back. This is another lecture in the series for ELIC 200, so electric machines. It's Mr. G here again. Today we're going to be talking about the basics of a transformer. So transformers, the ones we're going to be talking about are not robots in disguise. So we're going to be looking at a transformer, but not the kind from the movie. We're going to be looking at the kind that transforms electrical energy. So something that looks like this. So a basic power transformer. So if it's not a robot in disguise, what is a transformer? Well, if you think back to previous lectures when we talked about an electrical generator. An electrical generator, by definition, was a machine that converts mechanical energy into electrical energy. If we use that same thought process, a transformer is a machine because it does a job. So a transformer is a machine whose job it is to convert one form or level of electrical energy into another form or level of electrical energy. So electrical energy into electrical energy. So a transformer is a machine whose job it is to convert one level of electrical energy into a different level of electrical energy. So that is the basics of what a transformer's job is. Now this is a power transformer we're going to be talking about for this particular course. So again, electrical energy into electrical energy. There are three main components of a power transformer, a general power transformer. You have what's known as a primary coil. You have a secondary coil. And you have what's known as the core of the transformer. Now the core is normally a soft iron material that is thin pieces of iron that are laminated together, and normally it makes up some kind of a closed loop. So on one side we have the primary. On the other side we have the secondary. And then we have what's known as the core. So the core of the transformer. So the principles of a transformer work on something that is known as mutual induction. Mutual induction basically breaks down to a simple concept. one coil creates a magnetic field, and that same magnetic field causes something to happen on the other coil. So one coil creates a magnetic field. That same magnetic field has some kind of interaction and result on the secondary or the other coil. So both coils share the same magnetic field. It's the mutual magnetic field. So same magnetic field from here to here. So if we apply electricity, so AC waveform, if we apply it to the primary side, this coil will create a magnetic field. That magnetic field is referred to as the flux. So the flux actually flows through the core of the transformer and ends up flowing down through that secondary coil. So typically it's the Greek letter phi represents flux. So the primary creates a magnetic field known as a flux. When the primary creates a magnetic field, that magnetic field flows through the core. The core's job is to direct the magnetic field. So rather than having the magnetic field scatter in free space, the job of the core is to direct the magnetic field down through the secondary coil. So that magnetic field is put through this secondary coil. A voltage is then created on the secondary coil that's related to the strength of that magnetic field. So if we apply a voltage on the primary, so we basically, if I did this and put a voltage onto the primary, its job is to create that magnetic field. The magnetic field then flows through the core, then it flows through the secondary, and what appears out at the end of the secondary is a representation of a voltage. So this becomes the input, and this becomes the output. So what we've got, again, three main parts of the transformer. We got a primary and we have a secondary, and the two of them are linked together by this core, and the job of the core is to direct the magnetic field, or the flux, from one into the other. Something based on what's known as mutual induction. Right. So in transformers, there's something that's known as the general transformer equation. The general transformer equation has three sentences to it. The first one says that the flux in the core of the transformer links both the primary and the secondary windings. So if we go back to our diagram here, the flux in the core links both the primary and secondary windings. The next statement says, thus the mutual flux must set the same EMF in both windings. So if the flux is of certain strength, it will affect one winding the same as it affects the other winding. Since the turns in each winding are linked by the same flux, the EMF induced per turn must be the same in each coil. So, what the whole transformer equation means. So again, let me just read the whole thing one piece by piece. The general transformer equation: the flux in the core of the transformer links both the primary and secondary windings. Thus, the mutual flux must set the same EMF in both windings. Since the flux in each winding are linked by the turns in each winding are linked by the same flux, the EMF induced per turn must be the same in each coil. So, altogether, what that means is the flux links the primary and secondary coils. The flux has the same strength for each. Therefore, the flux created per turn here will be the same as what it creates as a voltage output here. So what that means is if I take an example, so here is a transformer. This is a symbol for a type of transformer. This is the primary side. This is the secondary side. This represents the iron core. So this is the schematic symbol for it. This flux is created by two things. It's created by the voltage and the number of turns. So the flux, we can say the flux is created by a voltage and the number of turns. So we can say this flux is created by whatever voltage we have here as an input and however many turns that coil is. That creates a certain flux. So let's pretend, just pretend, that we had 100 volts and we had 100 turns in the coil. We can make a statement that says that the flux that would be flowing here was created by 100 volts on 100 turns. So this is what actually created that flux. So 100 volts placed on 100 turns creates a certain amount of flux. If I put 200 volts on 100 turns, that would create more flux. If I put 50 volts on 100 turns, that would create less flux. So, basically, the magnetic field, or this flux, is based on two things: the voltage and the number of turns. So, if I said I have 100 volts and 100 turns, so that would be 1 volt per turn. So that translates into 1 volt per turn. So the flux that's going to be flowing here was created by 1 volt per turn. So now that flux flows here. It will now create a voltage on the secondary that is equal to 1 volt per turn. So, if this is what created it, it will then create a voltage that is based on this relationship. So, for our example, if I had 100 volts, 100 turns, the flux would be created at 1 volt per turn. That flux flows through this. It will create a voltage based on 1 volt for every turn. So again, the flux is created on the primary side at a particular value based on the voltage and the number of turns. That flux will flow through the secondary and it will create a voltage based on the flux and the number of turns. So that is the general transformer equation. And it works out to be a relationship. The primary voltage over the secondary voltage is equal to the primary turns over the secondary turns. So the N represents the number of turns So the number of turns in the primary and number of turns in the secondary. So basically what that says is, if I put in a voltage, a flux is created at a certain strength. That same strength flows through here, creating a voltage based on the windings. General transformer equation. Now, we are assuming a perfect system, what's known as an ideal transformer. And for the most part, what we're going to be looking at are such scenarios where it's an ideal transformer. No transformer is perfect. No machine is perfect. There are losses in this system. So where do the losses happen? Well, this coil has resistance. So there's heat loss in energy on this coil. So that's one. This coil has resistance. 2. Transferring the magnetic field from the actual coil into the flux. 3. Losses in the traveling of the flux. 4. Transferring the flux back into this magnetic or into this coil. 5. So in general, we can look at 5 different areas of loss. Again, resistance of this coil, resistance of this coil. Transferring the magnetic field that's been created here into the core. Losses in the core. And then transferring the magnetic field back into this coil to get our voltage. So 5 areas of losses. So for this course, the majority of the work we're going to be doing in our discussion, we're working with an ideal transformer. So we're going to say there are no losses in the system. Everything is perfect. But in real life, there are 5 areas of loss. So, what does the transformer look like? So if we take a mathematical example, we're going to say, here's the primary, and here is the secondary, and here is the core. So I'm going to say that we put in 120 volts of AC. We have a primary turns, so this would be E primary. This is N primary. So I'm going to say we have 100 turns. N of the secondary is going to be 50 turns. What is the voltage on the secondary? So we go back to our general transformer equation, and we say EP over ES equals NP over NS. And we would plug in our values in this case. So I would have EP is 120. We're looking for ES. Turns is 100 over turns 50. Solve for ES. So ES is going to be 60 volts. And that's how the general transformer equation works. So again, primary over secondary, primary over secondary. There are three main styles or types, if you will, of transformers that we're going to find, and then a couple of other ones that fit in. But the first one is what's referred to as a step-up transformer. So a step-up transformer is where you have smaller number of turns on the primary than what we have on the secondary. So E on the primary, E on the secondary. So a step-up transformer, you end up with a relationship where the primary voltage is less than the secondary voltage. So we are stepping up the voltage. The next one is when we have more windings on the primary than we do on the secondary. This is what's known as a step down transformer. And in this case, the primary is greater than the secondary. The last of the common ones you have E on the primary, E on the secondary, and this is called isolation transformer. In an isolation transformer, primary is equal to the secondary. So there's no increase or decrease of electricity. Okay, there's no increase or decrease in the electricity. They are equal. But what you get is isolation. So, what is isolation? In a typical power transformer, when we have those three components, so we have actually let's just go back to our diagram that we already did right here. We've got the primary side. We have the secondary side. What links the two is the flux. And that's it. So here, there is no electrical connection between the primary and the secondary side at all. The only thing that joins the two is a shared magnetic field. So there's no electrical connection from here to here or here to here. There's no wires that are touching each other, you can see. They are their own separate circuit. They are isolated from each other. The only thing that joins them is a magnetic field that they both share. If we look at a schematic version, it's the same thing. This circuit and this circuit are electrically isolated. Being electrically isolated is one of the big advantages, or one of the good things that happen in a transformer, is that things are electrically isolated. So if you wanted to electrically isolate something without changing the voltage, you would use an isolation transformer. Regular transformers do the isolation part as part of being a transformer. So they isolate and change the values of the voltages. Whereas an isolation transformer, you gain the isolation without changing the values of the voltage. So that is another type of transformer that is available to us. So the number of turns on each of those would be the same. So you'd have, as an example, 1,000 turns and 1,000 turns. So therefore the voltage that's spit out on the secondary is the same as the primary, but you gain the electrical isolation. Now the other types of transformers that we are going to be dealing with, power transformers, is ones that we refer to as a center tap transformer. So you have your typical primary, and then you're going to have a secondary, with a tap. So let's say we put in 12 volts and we got out from here to here. Let's pretend we got out 24 volts. If this was a center tap, then that means we would also get, that was 24, we'd also get 12 volts and 12 volts. There are transformers with many taps. So then we could get, let's pretend 6 and 6. So from one transformer we can get 24 volts, 12 volts, 6 volts, different values of output based on where we actually touch the coil. So this is what's known as a tapped transformer. So we can center tap it, which is right down the center, or we can tap it anywhere we like, and therefore on the secondary side we get more than one output voltage. So it's a tapped transformer. And the last one that we're going to cover in this class is what's known as an auto transformer. An auto transformer is a special type of transformer, and the auto transformer has only one shared coil. So basically an auto transformer is a specific type of transformer, and it kind of looks like this. So we've got a coil that comes like this. We have a core. If this was the input on the primary side, so we'll say input, the output is actually taken here and then typically a tap off of that coil like that. So an auto transformer share a coil. We can take an input. Normally they are a step down type transformer. Take an input and we step it down and we pull out another voltage coming off the coils. And this could be a 50% tap, an 80% tap, whatever it would be. But they share the same coil. So one thing that they are missing that the regular transformer gives you is the isolation. There's no isolation in an auto transformer because we're actually touching the same coil on the input and the output side. But typically, an auto transformer, because of its one shared coil and a smaller core, lighter, smaller, and cheaper to manufacture than this kind. So depending on what the application is, you can get a regular power transformer, 2 coils and a core. You get the electrical isolation. You can do step up. With the auto transformer, they're normally a step down. You do not get the electrical isolation, but what you do get is cheaper and smaller, so physically smaller transformers. So again, depending on what the application is, we've got something called an auto transformer. In a transformer, we have something that is known as the transformation ratio. Transformation ratio, not turns ratio, transformation ratio. Transformation ratio, the symbol that is used is A. And what it is, it's a relationship between the primary and the secondary side of the transformer, whether it be voltages or currents. Voltages or turns. Or currents. So, transformation ratio is primary voltage over secondary voltage, or primary turns over secondary turns, or 1 over A is given as the primary current over the secondary current. This is known as the transformation ratio, and again the symbol is A. So if we looked at our examples, a step-up transformer, so A would be a value of, if the primary is smaller than the secondary. Primary smaller than the secondary. So let's say 1 over 2. So therefore A in a step-up transformer would be less than 1. So A of less than 1 in a step-up transformer. In a step-down transformer, A is going to be greater than 1. In an isolation transformer, A is equal to 1. So in this case, both the voltages are the same. Both the turns are the same. In this case, more turns here, primary to secondary relationship. So more turns here, less turns there. A is going to be greater than 1. Here, less turns, more turns. It's going to be less than 1. So the transformation ratio is primary, or relationship, primary to secondary. Can also be looked at as 1 over when based on the currents. We're going to do an example, and hopefully this all comes into play for this example that we've got. So I'm going to take a transformer and we're going to make this a step-down transformer. And I am going to say, on this transformer, I'm putting 120 volts. And I'm going to say that A of this transformer is equal to 3. And I'm going to take this and I'm going to put it through a resistor. And I'm going to say the resistor is 1 kilo ohms. So what we're going to do is we are going to solve for this circuit. So in order for us to solve for the circuit, we need to be able to do certain things. One is we have to be able to calculate I primary. We need to calculate E secondary. We need to calculate I secondary. So we're given E primary, 120 volts. We're given A, which is the transformation ratio. So that is the relationship that exists between the primary and the secondary side. We're given a load sitting on the secondary side, and now we have to solve for the circuit. So solving means we're finding IP, IS, and ES. So we are looking for IP, we are looking for IS, and we are looking for ES. So those are the three values we need to calculate. We know that the transformation ratio is 3. So if we go back to our formula here, we can see that A, so bring this up, A is equal to E1 over E2. So E2 is your secondary, so there's your secondary. So sometimes you'll see primary as 1 and secondary as 2. Sometimes you will actually see it as EP or ES. Okay, primary is 1, secondary 2, or sometimes it's labeled as EP and ES. So in this case, ES is equal to, we're going to rearrange this formula and we're going to solve for E2 or ES. So basically we're going to take this side, we're going to multiply over there, and what it happens to be is E1 or E primary divided by A. So E primary is 120 volts, A is 3, therefore what's on the secondary is 40 volts. So we got 40 volts sitting here now. So Ohm's law will tell us we got 40 volts over 1K. That should give us an I secondary of Ohm's law. So we'll say ES divided by R. We'll say this is R. So that works out to be 40 divided by 1K, so that becomes 40 milliamps of current flowing. So now we need to find out what the current is on the primary. So what we're doing is we're working backwards, and we got to find out what this primary current is. Well, 1 over 3 is equal to the primary current, so IP, over the secondary current, which is 40 milliamps. So if we did that math, so basically we're looking for 1 over 3 is equal to, and we're going to solve, whoops, yes. What have I got here? IP is equal to, we got 1/3, okay, 1 over A is equal to I primary over the secondary. So now we're solving for I primary. And what do we end up with? Well, we do this math and we should end up with 40 divided by 3 equals 13.3 milliamps. 13.3 milliamps. So that's our simple calculation. We need to be able to prove that this is true. So I'm just going to move this up here for a second. If you remember from high school physics and the discussion that we've had in the last couple of lectures about the law of energy conversion, it says that energy cannot be created nor destroyed but only changed in form. So in the generator, we went from mechanical energy to electrical. Transformer, we go from electrical to electrical. Now, in the transformer, we're not creating anything new. So we're just transforming. So if this was a perfect machine, again, remember there are losses, but if this was a perfect machine, the energy you give in would be the same energy you get out. So what we do is we look at it as power in and power out of a transformer. If there are no losses, and we're going from electrical to electrical, power in is equal to power out. In a realistic situation, power in is equal to power out plus your losses. But if we're looking at a perfect system, losses we don't have. So power in equals power out. So if we go back to our calculation, that rule must apply. So let's check our answers. Power in. Power is voltage times current. So power in is the voltage in, 120, times the current. Current we figured was 13.3 milliamps. Power out, E times I. So the power out is 40 volts times 40 milliamps. Well, let's see if they work out to be the same. So 40 times 40 exponent 3 to the minus equals 1.6 watts. 1.6 watts. Now the other side must be the same. 120 times 13.3. Oops, sorry. 120 times 13.3, missed the button. 3 to the negative equals 1.6. So power in equals power out. So in this, for this all to happen, if I have a step up transformer, if my voltage goes up, my current goes down. So if my voltage increases onto the secondary, my secondary current must be smaller than the primary in order to keep power in equals power out. Step up. What about step down? Same concept. Step down. Voltage goes down. Current goes up. So that means I have more current available on the secondary. So I'm dropping the voltage, but getting more current. On an isolation transformer, so in isolation, we've got 1-to-1, so both the voltage and current remain. On both sides. And that's all because P in must be equal to P out. That rule must always be in play. Okay, so remember, in a realistic term, P in is equal to P out, and you got losses. But if we're not taking into account any losses and we're going with what they call the ideal transformer, P in equals P out. P in equals P out. An increase in voltage, a decrease in current. A decrease in voltage, an increase in current. Transformation ratio. Alrighty, so I hope this helps. We'll be doing some more questions in our Live with Mr. G session. So this is the basics for transformers. And again, not robots in disguise. So I hope this helps. Until next time, everybody stay safe. Take care.